Section 2.5, Part 2, Zeros of Polynomial Functions. Today we're going to begin by looking at the rational zero test. This test helps us identify possible zeros or roots of a polynomial equation. Now this is helpful because oftentimes we may not be able to factor when solving them, so this will help us get our first solution to kind of get that process going. So to do it, we have to look at the factors of our front number and our back number. So the leading coefficient has a bunch of factors, and so does the constant at the end. What we do is we basically create a fraction based off those. Okay, now the fractions that we're going to create, the numerators, they come from all the factors of the constant term, and that's usually the last number that's in the polynomial. The denominator is going to come up from factors of the leading coefficient. So we kind of look at this whole polynomial, we look at the back number and the front number, and we create all the possible rationals that could happen here. Now, another thing that should be pointed out is that each one of these can also be positive or negative. Now, this list can be quite long at times, but it does at least give us some place to start when we're looking for that first zero. So what we want to do once we've come up with this list is basically start testing to figure out which one in fact is a zero of the polynomial. Once we have that, we can of course divide it out and move on from there. So this is a really important first step because again, when you can't factor a polynomial equation, this is going to give us some numbers to start checking. Okay, otherwise we'd have really no place to start. Now it's also important to understand that this only works when you have integer coefficients. Okay, so if we have any sort of polynomial that has maybe complex numbers in it right away as coefficients, this would not work. Secondly, this only identifies rational zeros. Okay, so if you did have like an irrational zero like the square root of 3 as maybe being a zero, this would not show up in the list. So the hope is when solving the equation, at least one of the zeros that it has is rational and real. Okay, because obviously if we don't have that, it's going to have a tough time coming up with those. Okay, this is really just about identifying real rational zeros. But usually if we can get at least one, that can hopefully be enough to get the rest. Okay, so let's try this out. As far as a step-by-step process, I would say the first thing, of course, is identify possible zeros. Okay, and that's again using that rational zero test. Now, the second thing is we're going to use division, okay, specifically synthetic division, to identify which of those in that list is a factor. Okay, and again, it's a little bit of a process of elimination, but at least you have a list to work off of as opposed to just randomly guessing values. Now, once you figure out at least one factor, you can keep repeating that if needed, or if the result is factorable, you keep going until you fully factor the polynomial. And once that's done, of course, you can use the zero product property to get all the solutions. Okay, so in our first example, we have a cubic, right? 2x cubed plus 3x squared minus 1. So the first thing we want to do, of course, is look at all the factors of the back number. Well, in this case, it's just 1. Now, the factors of the front number, right, are 2 and 1. Those are the numbers that go into that. So in order to come up with what are the possible rational zeros, right, there could be solutions to this polynomial, we're going to take all the factors of 1 and divide it by all the factors of 2. So basically 1 divided by 2 and 1 divided by 1. And again, each one of those could be positive or negative. So if I take 1 divided by 1, I have a 1, and again, it could be positive or negative. If I take 1 divided by 2, right, we'll get 1/2, and again, it could be positive or negative 1/2. So these four numbers represent possible rational real solutions to the polynomial. So it might be a 1 or a negative 1, it could be a 1/2 or negative 1/2. I don't know, but it's my job to check. So again, to do that, we're going to go to synthetic divisions. So when we set this up, obviously we'll have a 2, a 3, a 0, and a negative 1. Now, I don't have any wonderful advice as far as which ones to start with. Honestly, I just kind of start at the top of the list and we'll work my way down. Oftentimes, I'll do the integers first just because I think it's faster. But don't be afraid to check the fractions as well, right? Things that don't look like integers. If they could be zeros as well. So I'm just going to start with 1, then negative 1, then check 1/2, negative 1/2 until I find a solution. So let's begin with positive 1. So when I put a positive 1 in here, right, we drop our 2. 2 times 1 gives me that. And then we get a 5. 5 times 1 is 5, and you add it. And right about here, you should really notice this isn't going to give me a 0 remainder. Because obviously I'm going to get a 5 here. So when you add, you get 4. That's not a 0 remainder. So what I can take away from that is positive 1 is not going to work. So we just have to start over. And this time, let's just move down the list. Now let's check negative 1. So drop down a 2, and then of course we get negative 2, positive 1, negative 1, negative 1, positive 1, 0. Okay, so it looks like while 1 didn't work, negative 1 is in fact a 0 for this. So what I can say now, kind of moving forward, as far as rewriting my polynomial, I can say that this polynomial here so far, because -1 is a 0, that means x plus 1 must be a factor. Now we have to look at what's left, right? So in this case, remember this, our quotient is what's left after I divide out the x plus 1. So once you identify your first 0 and you get your first factor, you can think about, well, the quotient is the what's remaining here. So I'm going to go ahead and write that down. We have, 2x squared plus 1x minus 1. Now, at this point in time, because I am down to a quadratic, I no longer need to do synthetic division, because either I can factor this or I can use a quadratic formula, okay? Because once you get down to a quadratic, it doesn't really matter about testing anymore because you're always able to solve quadratics. So again, it's my choice. I can either factor this if it's factorable, or if it's not factorable, I need to use a quadratic formula to go ahead and figure out what those other two zeros are, because they could be irrational, they could be complex, right? There could be some imaginary numbers. So you never know, but just do the best you can. So for this problem, I do notice it is factorable, so I'm going to go ahead and do that. So 2x squared plus x minus 1 factors to, we have a 2x in the front of that one and x here, and then of course we need factors of 1 to make 1, and then as long as we put a negative here and a positive here, we'll end up with that positive 1. So now that I've come up with all my factors, now I can come up with my solutions. Okay, now remember, we already knew -1 was an answer. If I solve the second term here for 0, that would be adding 1 divided by 2, so looks like positive 1/2 was. And of course, -1 also happens again. Okay, so I can go ahead and write it this way, or if you want, you could, of course, just leave this out and just refer to the -1 as having a multiplicity of 2. Okay, let's try this again. This time, we're going to solve a 4th degree polynomial. Okay, and instead of like this example that's just listed off here as a polynomial, let's find the zeros, now it's actually written as an equation, but we're going to use the same process. So looking at the factors of our constant, we have 1, 2, 3, and 6. Now the front leading number is a 1, so that's actually really helpful. So when I look at all the factors of this number divided by this number, it's basically 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. So we don't have any fractions, right? They'll all be integer values. So let's go ahead and list out the possibles. Now remember, all of these could be positive or negative. So it's positive -1 divided by 1, positive -2 divided by 1, and 3 divided by 1, and positive -6 divided by 1. Okay, so again, now we have to go ahead and check. So we're going to do our synthetic division. All right, so with this one, we have a 1, a 1, a 1, a 3, and a -6. So let's go ahead and just start at the top of the list, right? See what we can do here. In this one, it looks like we'll start with positive 1. Try it out. So if I go ahead and drop my 1 down, you get 1. 1 times 1 is 1. Add, you get 2, and 2, and then 3, 3, 6. And actually, look at that. We lucked out. It looks like our very first try did give us a 0. And that's nice. Sometimes that can happen. Okay, but again, if this didn't work, move down the list. Try -1. If that doesn't work, try 2. Try -2. Keep going, until you get one. Now, at this point in time, let's take a look at what we got, right? We have x minus 1 as a factor, because we just discovered 1 was that, So when we solve this for 0, let's see what's left. We have 1x cubed plus 2x squared plus 3x plus 6. Okay. Now, at this point in time, you have a choice, and this is the same as before. If you can factor this, that might be a good idea. Now, if you don't want to factor it or it's unfactorable, you have to go back to the list and start over again. Okay, now that being said, notice how this still has a 6 here and this still has a 1 here, so they have the same possibles. Essentially, you kind of start over with a brand new problem by looking at what are the possible zeros of this. Okay, so there may be times at this point in time you get to having to do this process again. But again, if you can factor or do anything else, you want to, okay, because we have to at least get down to a quadratic. Now, what I noticed, though, is that in the first two terms here, if I take an x squared out, that leaves me with x plus 2. Over here, if I take a 3 out, I also can get an x plus 2. So by noticing that, this can actually be factored by grouping. So I can go ahead and leave this x minus 1 here. But again, if I take an x squared out of the first two, I can get an x plus 2 out of both groups. So when I take an x plus 2 out of the first group here, that's going to leave me with that x squared. Taking x plus 2 out of the second group is going to give me that positive 3. Okay, and I did that kind of in one step in my head. If you need to, when you do your grouping, show a little more work there, that's fine, but this is what's going to happen. Now, if you looked at this and you didn't recognize you could do grouping and you went back and started checking, right, notice -2 is a 0. So maybe it would have taken you 1, 2, maybe 3 or 4 different tries real quick in synthetic division, but you would have been able to come up with another 0 and then had the quadratic left over. Now, I will point out the zeros of this one are imaginary. So clearly, there are only 2 rationals. But again, that would have been enough to get us from a 4th degree, down to the quadratic. So to finish this out, let's go and get our answers, right? So we have 4 of them. The first one, of course, is +1. Our second answer is going to be -2. And then, of course, when we solve this quadratic right here, we're going to subtract 3 and then square root. So again, when you write that with i's, right, that's going to be x equals positive or negative I radical 3. Okay, and again, that's because over here, when you solve for x squared, you get -3. And when you take the square root of that, you get that radical of -3. So remember, we have to put that I there. Now, the last little thing we want to talk about as far as solutions is something called Descartes' rule of signs. So this is basically a really fast, easy test to let us know roughly how many possible, positive real zeros or negative real zeros a polynomial may have. And this can sometimes be really helpful because if you do this test and discover perhaps maybe it may not have any real zeros, that can help you point down the right direction of maybe there's only complex zeros. Or, depending how this works, you may notice, hey, this thing only has real positive zeros. Maybe there aren't any negative ones. And if that's the case, sometimes that can help you narrow down that possible list of what you're testing, okay, especially when you have a longer list to look at. Likewise, maybe it's only zeros, okay? So this is really all about identifying, as far as real zeros, right, whether you have a number of positive or negative ones, okay? Now, just like our previous rational zero test, this only works, of course, when you have real number coefficients. Okay, so that means obviously if you have a polynomial that already has complex numbers as coefficients, this would not work. Also, obviously your constant cannot be 1. Okay, just a little bit of a rule that kind of has to happen there. Okay, so basically what we do is this. Okay, so we're going to look at f of x and we're going to look at f of negative x. And this is the same thing we did when we looked at symmetry of a graph. So we obviously have f of x given to us. The only real work algebraically that we have to do is figure out what does f of negative x look like. Now again, just like before, when you plug negative x into the function, that really just changes the sign of all the odd powers and keeps the even powers the same. Okay, so that's a little shortcut to see what that looks like. Now once you can see f of x and f of negative x in front of you, you first start with f of x and basically count how many sign changes are there going from one term to the next. And however many sign changes there are, that's how many possible positive zeros you have, or less than that by an even. So what I mean by that is, let's say you count 2 sign changes. Okay, so that means you could have a possible 2 positive real zeros, or 0, because again, it could be less than that by an even number. So let's say we had a really big polynomial, and there was 7 sign changes in f of x. Okay, so if there were 7 sign changes in f of x, you could have 7 positive real zeros, 5 positive real zeros, 3, or 1 positive real zeros. So if you notice, basically however many sign changes is like the maximum number, and then you just take away 2 until you can't anymore. So that gives you all the possibilities. And the same is true when looking at f of negative x, right? If you look at the sign changes of f of negative x, that will be the maximum number of possible negative real zeros, or again, less that by an even number. So again, let's say you were looking at f of negative x, and it had 3 sign changes. Then you could have a possibility of 3 or 1 negative real zeros. Okay, let's try this out. In our first example, we have a 4th degree. So the first thing I want to do, since I already have f of x, is figure out what does f of negative x look like. Now, as a reminder, when you do this, you're basically plugging in negative x for all these x's, okay? Now, the thing is, when I do this, I'm going to go ahead and show my work on this first one, but something I want you to notice, just as something to make this go a little faster in the future, is that when I simplify this, you'll notice every single x that is an even power doesn't really change, right? And all the ones that are an odd power do. So if I simplify this, if you have negative x to the 4th, that's still just going to be x to the 4th. See how it didn't change? But if I take negative x to the 3rd, that's actually negative x cubed, which makes this a positive 3x cubed. Okay, so see how the odd power does change? Likewise over here, and I don't know why I didn't write this here. Let's get this negative x in here, right? If you take negative x and square it, again, that's not going to change. It's still just x squared. So this is going to remain positive 6x squared. But having a negative x times the 2, right, makes it negative 2x. So just as a little shortcut, when you're replacing all your x's here inside the polynomial with negative x's, the odd powers, like the third power here and the first power here, they're the only ones that actually change. Evens do not change. They'll remain the same. Okay, so let's count sign changes. Let's start with f of x. So in f of x, we start positive to negative, so there's a sign change. And then we go to positive, so there's another sign change. Then we stay positive, but then we go to negative. Okay, so for this polynomial here, if we're looking for what are the possible number of positive real zeros, we obviously have a maximum number of 3 sign changes, or we could subtract 2. Maybe there's only 1. Okay, so as far as positive real zeros, we could have either 3 or 1. Now what that tells me is that there's going to be at least one positive 0, right? There's either 3 of them or 1 of them. There's not a possibility of having 0. Now let's count how many possible negative real zeros we have. Okay, so going over here to f of x, we go from positive to positive to positive to negative. So there's our first sign change. But that's the only sign change, right? We stay negative after that. So that means there's 1 negative real 0. And I can't take away 2 from 1, so I know for a fact there is going to be 1 negative real 0, okay? So my possibilities basically are this, right? I could have 3 positive zeros and 1 negative 0, right? And that would be all 4 of them. Or I could have 1 positive and 1 negative. Now, if that's the case, and that's only 2 of the zeros, that means the other 2 zeros would be imaginary. Okay, let's try this again. Again, we have f of x. We're going to write what does f of negative x look like. Now this time I'm going to take advantage of my shortcut and just realize when I do this that all the signs of the odd-powered x's are going to change and all the signs of the even-powered x's don't. So we're going to make this negative 3x to the third. We're going to keep this, right, not change it, negative 5x squared. We're going to change this one to negative 6x and of course plus 4. Okay, now we're going to count sign changes. So looking at our first function, we go from positive to negative, there's a sign change, to positive, there's another sign change. So as far as possible numbers of positive real zeros, we have 2 or 0. Okay, so we either have 2 of them or none of them. Looking at sign changes of f of negative x, we start negative, and then we're negative, continue negative, and it looks like we have 1 sign change. So that means as far as negatives again, we only have 1. So the possibilities here, of course, would be that we have either 2 positive zeros and 1 negative 0 for the 3, or maybe we have 0 positive, 1 negative for the 3, which again would mean the other 2 would be imaginary, which makes sense because, of course, imaginary complex zeros always happen in conjugate pairs.